Hi, my name is Jim, and today we're going to be talking about equipment loading. Particularly when you connect a piece of test equipment to a circuit, it's going to make some kind of change in the circuit, and we kind of need to know what that is, and if we can, to minimize it. Equipment is your eyes and ears into a circuit, so if you're designing or troubleshooting something, it kind of tells you what's going on, so you can make the appropriate decision on what to do, how to proceed with whatever it is you're trying to accomplish. So we're going to start here with scope probes, and here we have a probe. It's got a ground clip. For high frequencies, important is this to be as short as possible. This is actually an antenna. It has a little clip on it and a little switch called X1 and X10. So in X1 times 1, this is basically a piece of wire. It connects the BNC connector directly to the scope probe. In X10, that's times 10, it has a 9 meg resistor in the base of this, along with a variable capacitor that basically increases the impedance of the scope at DC and low frequency levels by a factor of 10. And for high frequencies, maintains that 10% division ratio, so we don't get any alteration with regard to the higher frequency components in a signal compared to the lower frequency components. So I guess we could say the gain of this here would be 0.1, and it definitely reduces loading. However, there's a cost to it, and that is that the sensitivity of the scope is reduced by a factor of 10. So if the most sensitive setting on a scope is 10 millivolts, and we use one of these in the X10 position, it's now 100 millivolts. So we'll talk about making the adjustments to compensate a probe, and you always use a plastic tool in this, and it's provided with the scope probe. And fortunately, the adjustments are very, very easy to make. But before we get into that, let's take a little look at a couple signals here. We have a sine wave, and this is as we typically view it in the time domain, where the abscissa is equal to time, and we're going to be comparing it with a 50% duty cycle pulse, which is called a square wave, as you can see here. Now we're also going to introduce the frequency domain, where in quadrant 1 only, this is the frequency and this would represent the amplitude, and I'm showing a spectral component here, a spectral spike at 1 kilohertz. So a pure sine wave would be represented by 1 spectral spike. Now a square wave, on the other hand, is a bit more complex. Actually, a whole lot more complex. It's not only made up of its fundamental frequency, where the period of both of these would be the same, but it also has a sine wave component of 3K, 5K, 7K, 9K, 11K, all the way out to infinity. Well, if it were perfect anyway. So what we can see from this is that the relationship of these harmonics, and a harmonic is anything that's above the fundamental, and this is going to be an even or odd multiple of it, contribute to the shape of the pulse. Now to kind of get a better feel from this, I've started out making our square wave here by drawing a 1 kilohertz sine wave in red, and then in blue I've added in the third harmonic, which as we'll see later is going to be equal to 1/3 the amplitude of the fundamental. And if we add these together, is what we get is something shown in the green, and if you kind of use your imagination on that, you should be able to see that it's squaring up a little bit. If we add in the 5th and the 7th and the 9th, it'll become square and square and square, until in a perfect square wave the rise time and fall time is 0, and that's called a discontinuity. So mathematically we can't represent that, but there is no such thing as a perfect square wave. It's always going to have a measurable, or at least a real world, rise time and fall time. Rise time is the time it takes to get from 10% to 90%, and fall time is from 90% to 10%. But we'll discuss that later. So as we can see that the waveforms not only look different, but they have a very, very different harmonic signature. Now to take a listen to this, I'm going to come over and let you hear a 1 kilohertz sine wave, and now a square wave, sine wave, square wave. So the difference we have in the different sounds of the two are caused by the harmonics. And that was both the same frequency and about the same level. So it obviously makes a big difference. And what you can think about is, why does a violin playing some fundamental note sound different than a guitar? And the answer is, the harmonics of the instruments are different. So keeping that in mind, let's very briefly talk about compensating a probe. And what we can do is take a look at a scope response where the low frequency and high frequency components are out of balance. And if I were looking at this with it undercompensated, what I would see would be a square wave which would look like this. Now, this rounding here means that the low frequency components, that's down here, are less than the high frequency components. And it also means, if you were to make a measurement on a system, not with a square wave but with any signal, is that the scope probe, depending upon where you were, would be misrepresenting the actual amplitude of the signal. In other words, you'd be being lied to. Now, if I stick my little tool in that scope probe and overcompensate it, I'm going to get something that looks like this. So what we can see here is, because these edges are steeper, is that the higher frequency components are higher than they should be. And that means if you make a measurement on some higher frequency signal, it's going to appear to be higher in amplitude than it should be. And again, you're going to be making determinations on what's going on in a circuit, and both of these cases can misrepresent what's actually happening. So when you compensate a scope probe, is you take the actual clip on the probe and you connect it to a little terminal on the front end of the scope, and it has a square wave. Usually it's a 0.5 volt peak to peak, 1 kilohertz, and all you have to do is take that plastic tool, insert it in that little screw device, and adjust it for as square as it can be, and you're finished. So it's a very simple manner to do that, and then we're going to talk about how that scope probe loads down a circuit in a minute. Never assume that a probe has been compensated. You always assume that it hasn't been. It takes a second to connect it, get the tool, and adjust it, and then you know. So, in a quick review, if we use an X10 probe, we're reducing the scope's loading on a circuit, meaning that the scope is going to change the voltage and or current or whatever to some degree, and then the question we're going to talk about next is how much. So if we go back and we're going to take a simple circuit here, we're going to be looking at low frequencies, direct current first. And this is our source here. It's comprised of two resistors, 2.2 meg and a 1.5 meg, relatively large. And this is kind of what our scope looks like, and I'm not including any of the capacity that's involved in this, because scope has stray. That's not a physical part, stray capacity on the input that we have to take into account, but we're not worried about that right now. So what we see is that the probe is in the X1 position, and that simply means that the X1 switch is shorting out a 9 meg ohm resistor. And you can kind of see by looking at this is a 1 to 10 divider, a voltage divider, and a scope input impedance is typically 1 megahertz, as is a DMM. So if we go to take a look at this, we can find the voltage across R2 theoretical is applying voltage divider. We end up with 4.54 volts peak, and if we measure that, that's what we would like to see. Now, will we? Well, I don't know. I'll have to find that out. So let's measure the voltage across our resistor here, R2, with a scope in the X1 mode, and then what we see here is that the scope's input resistance, in this case the 1 meg, is in parallel with our 1.5 meg. So the equivalent circuit, when the scope is connected, has this effective resistance at 600 kilo ohms. So it's changed the circuit quite a bit. Now if we go to measure what the output voltage will be, using voltage divider again, we'll actually measure 2.14 volts peak. And that's pretty far away from this guy. Well, that's 50%. That's not too good. And if we go to calculate the percent of error, which is V theoretical minus V measured divided by V theoretical times 100%, is that comes out to be a whopping 52.92% error. Very, very significant. Bad. So by measuring the voltage with a scope, we can be misled to believe that there's something wrong with the circuit. Now, keep in mind that this is a simple resistive circuit here that is used to model other electronics, perhaps op amps or whatever. So it's, it's not very exciting measuring resistors, but this is representing another circuit. Now, in general, the higher the resistance / impedance that you're monitoring, the more your equipment is going to load it. Also, the higher its operating frequency, the more your equipment is going to load it. So, having said that, this is in the X1 position. Let's take a look and see what happens in the X10 position. And again, that'll be for low frequencies or DC. And DC on your scope stands for direct coupling. So it will deflect with DC voltages. So now I've got the switch set in the X10 position. The switch is opened and the total resistance of the scope looking in here is 10 megohms. And the scope at this particular point would be saying 1/10 of what would be at the actual tip of the probe. And we're going to insert it and measure voltage across that 1.5 megohm resistor again. And let's see what the percent of error is when we have it in X10. So, placing that 10 meg in parallel with the 1.5 megohms and using voltage divider here, or product over sum rather, gives us a total of 1.3 megohms, which is understandably closer to the 1.5 meg is physically in the circuit. So, doing voltage divider again, we end up measuring 3.73 volts. And then calculating the percent of error on that, we see it drop from 50-something down to 17.8, which is considerably better. So in summary, what we have is the unloaded voltage is 4.54 volts peak, and the error actually would be 0%. We're not measuring anything, we're not loading it down. And then in the X1 position of the probe, where the input resistance of the scope is 1 megohm, we would be measuring, the scope would be telling us this, 2.14 volts peak, and that comes in at 52.92% error. And then finally in the X10 position, we'd be measuring 3.73, which is a lot closer to the theoretical, and that error would be improved to 17.8%. Now there are scopes that have times 100 and times 1000 probes on them also, but what we have is we're just concerning ourselves with times 1 and times 10. So that's kind of the story on loading, and what the message here is, and I'll repeat this later, is you kind of have to know about loading if you're making measurements in equipment. You're throwing widgets out the door because they're testing bad when they're not bad. It's just that your scope is loading down whatever voltage at a test point you may be wanting to measure. So the complete picture here is a bit more involved, and what we have in the scope actually is a nominal 20 picofarad of stray capacity, and that includes the capacity of the cable, its coax, so the capacity between the center conductor and the shield, and any wiring to the chassis of the scope would be a component of it, and so forth. It's variable. We don't know what it is. And that's why we make the compensation capacitor, and that's what this screw that I showed you in the base of the probe actually adjusts, is a CX, which is in parallel with the 9 meg. Now the objective of compensating a probe is that at low frequencies we have a 1/10 voltage divider here, and at high frequencies we want that to be the same. So whatever CX is, and we'll calculate that later, what we want is 9 parts of the signal at the high frequencies to be dropped across him and 1/10 across the actual stray capacity. So when we do that, the scope is not going to be discriminating in what it's displaying from the standpoint of the frequency components of the signal. Now, the overall impedance of the scope looking in here at higher frequencies is going to decrease because we clearly have two capacitors, albeit in series. But the relationship between the low and high frequencies when the scope is compensated will be the same. So if we wanted to solve this, what our equivalent circuit would look like would be this, and all I've done is remove the switch and so forth. We have 20 picofarad in parallel with our 1 meg, and I'm showing this in parallel with 11K. This guy, R2, and then it's just a question of doing some AC circuit analysis to figure this out. And if I determine, in this case I'm running 5 megahertz, the capacitive reactance comes out to be 1.592 kiloohms. And where I want to start here is the easiest place by taking these two resistors in parallel. And I'm going to use product over sum on this case, which gives us a total resistance of 10.88 kiloohms. So it's a little bit under 11K. So the next thing I need to do is I have one resistor represented by this, and then I need to put C in parallel with it. So that would be our equivalent. That's the two resistors in parallel with the capacitive reactance of our nominal 20 picofarad capacitor. And that's showing us product over sum here. And we have to be careful of the denominator because the sum is going to be adding a real to an imaginary. So we have to use the square root of the sum of the squares. And that'll give us in polar form these values here. And when we do the division, we find out that the impedance is 1.574 at negative 81.86 degrees kiloohms. Now, what that includes is going to be all of this. So, what you're talking about here is an AC circuits problem of basically 4 parts. So even though this looks like a lot of writing on the board, it really is straightforward stuff. Put the two R's in parallel, then put the equivalent R in parallel with C, and then we'll deal with this guy coming up in a minute. So what we need to do, since we're going to be putting this impedance, which is this guy here, in series with this, is to convert it into an equivalent series form. Again, back to AC circuits, all we have to do is take the real part times the cosine, or take the magnitude times the cosine, gives us the real part, and the magnitude times the sine will give us the imaginary part. Now doing that gives us a real part of 223 ohms, and the imaginary part comes out to be negative J 1.58 kiloohms. So it's highly capacitive. That's what this is telling us about this circuit here. Is the C is really kind of dominating, as you can see by the equivalent series resistance. And this is what it looks like. So we started out with a parallel guy, and we simply convert into a series guy. And the purpose of doing that is so, again, we can put them in series with our 11K and find out the voltage at this point right there. So, not too bad. And this is what our circuit looks like. And this here part is going to be comprised of the 11K, R2, the 1 megohm, and the 20 picofarad stray capacity. So if I want to use voltage divider to find out exactly what my measurement is going to be, I'm going to have to know what the total impedance is. It's going to be this Z divided by Z total. So Z total, I'm going to add the real and the imaginaries together, and the 223 isn't going to be much of a contribution in squaring it, and then adding in the value of 1.58 k ohms, and I'm not worried about the negative J here. And I've included the tangent operator here, and I'm not really concerned about that because all I want to do is to know what the scope is going to display. So what this gives us for Z total is 11.33K, and it's sitting at 8.019 degrees ohms. We don't care about anyway. So finally, what we would measure at R2 under this circumstance would be the ratio of this impedance to the total impedance times our source voltage, 12.8 volts, and that comes in measuring 1.77 volts peak. So what the voltage should be, the theoretical voltage should be 6.4 volts. And what are we measuring? 1.77. Significant trouble. This is with the X1 probe. Bad. Really bad. So if we go to find the percent of error, we have the theoretical time to measured times 100%, and we get 72.3% error. And most of the error, again, is caused by the 20 picofarad stray capacity. Really not wanted. Two conductors separated by an insulator's capacity. That's the way it works. So let's take one more look at this, and now we'll include this in X10, and we'll assume that the probe is compensated. And what I've done is taken a liberty here, and what I know is that when this probe is compensated, the resistive value is going to be 1/10 relative to the input, and the capacitor value of Cx, which is variable, is also going to be 1/10. So since the ratio of 9 meg to 1 meg is the same as the ratio of X sub Cx to X sub C 20 picofarad, I can break them apart. And by doing so, it makes the calculations a little bit easier. So it's okay to do that, and now what I want to do is find out what the capacitor voltage divider is going to be. Say 1 volt in, 0.1 volt out. X sub Cx, this guy, again variable, is going to be equal to 9 times X of the 20 picofarad. 9 and 1 meg, ratio of these two are going to be the same. So that's kind of an important understanding of the way this is going to work. Is the capacitance ratio has to be the same as the resistive ratio. So what is XCX? Well, let's go figure that out here. And what we could say is that XCX plus X of 20 picofarad is going to be equal to 10 times the reactance of 20 picofarad. And this is going to kind of assume here that this is going to be 9 X sub C. X sub Cx is going to be 9 times the reactance of this guy. Again, 9 to 1. So kind of chugging through here and moving things around a little bit, I can set up the equation, and then I can divide out 2 pi f 1 over Cx equals 9 over C20, and then by solving for Cx, it turns out to be 2.222 picofarad. So that would be the value of this guy right here, 2.22 pf, when it is compensated correctly. And that means that the reactance of this at any frequency is going to be 9 times the reactance of this at that frequency. So as long as we keep that ratio in shape, our square wave will be square. The scope will not be discriminating between low and high frequencies. So let's see how this actually works in a circuit here. We'll make the calculations, and this time we'll try to reduce the amount of work. What I'm going to do is Thevenize our source here, and this will just give me one resistor that I can connect to our probe circuit. That's this guy. And to Thevenize, what you do is you have the open circuit voltage, and I don't have a probe connected, so I'm going to call that open circuit. And in this case, as you can see, it's just going to be a 1 to 2 voltage divider, so VTH is going to be equal to 6.4 volts. Now to find RTH, you replace the source by its internal impedance, and for a voltage source, the internal impedance is 0 ohms. So if I take this and short it out, look into this point, what I see is 11K in parallel with 11K, which gives us 5.5 kiloohms. So the Thevenin equivalent circuit is this guy right here. And should this be a current source, its internal impedance is infinity. So it actually just opened that up. But it's voltage source, so it's 0 ohms. So here's our Thevenized source, and now we're going to connect our probe down to it. And this is kind of the simplified version of it. And what I want to do first, I suppose, would be find out what C total is. And I started off here and wasn't pleased with that, so I backed up and started over again. So we have two capacitors in series, and unlike resistors or inductors, we do not add them together. That's going to be product over the sum for the case of 2. So solving for the total capacity into the compensated probe ends up being 2.0 picofarad. So the capacitive reactance of this in series with this turns out to be 1591, 15,915 ohms, 15.9 k ohms. So now we're in position to find out what the impedance of this will be, and we work through that. Basically, the capacitive reactance is so much lower than that of the resistance that it dominates the circuit, and the math here basically comes out showing that to be almost 100% capacitive. Realistically, this is negative 89 something. So I'm just going to show it as 15.9K at negative 90 degrees ohms. So it has a very capacitive flavor, and if I were to reduce the frequency here from 5 megahertz lower, then my denominator here would become more resistive and less capacitive. But the values I chose here just turned out to be that it's dominated by the lower impedance path through C. Now remember, we still have a 1 to 10 voltage divider, resistive and capacitive legs. Okay, so this is kind of what we have now. This is effectively the scope probe, which, as stated before, was mostly capacitive, and this is our Thevenized circuit here. So all I have to do is apply voltage divider to this, and things fall apart pretty quickly. In the numerator, I want the voltage across what was our R2 here, which has been incorporated into the Thevenin circuit in this case. And that's going to be 15.9K. I'm not showing any angles in here, don't have to, not interested in phase. But in the denominator, I have to add these in quadrature because we have a real component and an imaginary component. So that turns out to be 6.4 times our 15.9K over 16.84K. You can kind of see by these ratios that this isn't too far away from unity, and unity is a good thing. So figuring that out, it comes out to be 6.04 volts. Now, the last step I need to do is figure out the percent of error, and I'm going to do that by the V theoretical instead of Thevenin. This is theoretical here. Minus V measured times 100%, and putting in the numbers, I find out that my error is 5.625%. So it's considerably lower than what we had before with the X1 probe, as opposed to a compensating X10 probe. So in summary, theoretical voltage is 6.4 volts. The X1 probe allowed us to measure 1.77 volts, which turned out to be a 72.3% error. And with the compensated X10 probe, it turned out to be 6.04 volts, which gives us 5.625% error. So you're always going to have error. Always. The question is, how bad, and did you take it into account? Do you need to take it into account? If these resistors were very, very low in value and the frequency were very low, probably wouldn't have to worry about it. Also with a DMM, remember that the leads aren't shielded like a scope probe lead is. Now they call an unshielded lead today word antenna. So you have to be very careful when you're using DMMs, especially across high impedance circuit components, that the induced signal from the 60 Hertz 120 hertz associated with the wiring in the building and whatever else doesn't interfere with your circuit. Measuring an oscillator will often kill it if it's operating at frequencies. So anyway, that's the overview on calibrating a scope probe and some of the math that sits behind it. And remember to do that. And I suppose the most difficult part is finding the tool. Do not use an external square wave generator. Always use the square wave on the front of the scope. So that'll do it, and thank you for watching.